Quantum mechanics. It's the science that rewrites what we know about reality. The rules of this tiny world, governing everything from atoms to subatomic particles, defy logic and challenge our perceptions of the universe. Today, we'll unravel the mysteries of quantum mechanics, exploring why this field is both thrilling and incredibly complex. Let's dive in. At its core, quantum mechanics is a branch of physics that studies the smallest particles in existence. We're talking about electrons, photons, and atoms, particles so tiny that we can't see them with the naked eye. Unlike classical physics, which explains everyday phenomena like the motion of cars or the orbit of planets, quantum mechanics operates on a micro level where the rules of reality seem different. In classical physics, the world is predictable. Drop a ball, and gravity pulls it down. Throw it, and it follows a defined path. But in quantum mechanics, predictability gives way to probability. The behavior of particles becomes a game of chances, where things can exist in multiple places at once, move unpredictably, and even influence each other from far away. That's why quantum mechanics is both perplexing and awe-inspiring. To understand quantum mechanics, we first need to grasp its foundational ideas. These principles redefine how we think about matter and energy at the smallest scales. Wave-particle duality. One of the biggest surprises in quantum mechanics is the concept of wave-particle duality. Imagine an electron. We usually think of it as a tiny point, a particle. But experiments show that it can also behave like a wave, spreading out and creating interference patterns, just like ripples in water. It's as if the electron can't decide whether it's a particle or a wave, it's both. This duality, where particles act like waves, lies at the heart of quantum mechanics. It was first discovered in the famous double-slit experiment, where particles were fired at a screen with two slits. Instead of forming two simple patterns, they created an interference pattern, proving that particles have wave-like properties. Quantum states and probability. In the quantum world, particles don't have a definite position or momentum until we measure them. Instead, they exist in a state of probabilities, described by a mathematical function known as the wave function. The wave function gives us the likelihood of finding a particle in a particular place or state, but it doesn't tell us exactly where it is. Superposition. Superposition is another mind-bending concept. It suggests that particles, like electrons, can exist in multiple states simultaneously. Imagine flipping a coin. In classical physics, it's either heads or tails. But in quantum mechanics, it can be both at the same time, at least until we observe it. With the basics in mind, let's explore some of the key principles that define quantum mechanics. Heisenberg's uncertainty principle. Werner Heisenberg's uncertainty principle is one of the cornerstones of quantum theory. It states that we cannot know both the position and the momentum of a particle with absolute precision. The more accurately we measure one, the less accurately we can measure the other. This isn't just a limitation of our measurement tools, it's a fundamental property of the quantum world. In a way, it means that the quantum world keeps some of its secrets hidden, no matter how advanced our technology gets. Quantum entanglement. Perhaps the most mysterious phenomenon in quantum mechanics is entanglement. When two particles become entangled, they form a connection that allows them to share information instantly, regardless of distance. If we change the state of one particle, the other particle's state will change as well, even if they're light years apart. Einstein famously called this spooky action at a distance. To this day, entanglement remains one of the greatest mysteries in physics, challenging our understanding of locality and connection in the universe. In quantum mechanics, particles are more than just tiny points, they're excitations in fields that stretch across space. Picture an invisible field spread throughout the universe. When you observe a particle like an electron, what you're really seeing is a small ripple in that field. This perspective, known as quantum field theory, suggests that everything in the universe, including particles, forces, and even empty space, is interconnected through these fields. In a way, quantum mechanics reveals a universe woven together by invisible threads. To fully understand quantum mechanics, we have to look back at its history. It all started with Max Planck in 1900. Planck discovered that energy is not continuous, but comes in small discrete packets called quanta. This idea was radical. It challenged the very foundations of physics. Soon after, Einstein expanded on Planck's ideas to explain the photoelectric effect, proving that light could behave as particles or photons in certain conditions. This duality of light sparked a revolution in physics. Niels Bohr then introduced the quantum model of the atom, and Erwin Schrödinger developed the Schrödinger equation, a mathematical framework that describes how quantum states change over time. Quantum mechanics isn't just theoretical. It underpins much of modern technology. For instance, transistors, the tiny switches that form the foundation of computers and smartphones, rely on principles of quantum mechanics. Without quantum mechanics, we wouldn't have the digital world we live in today. Quantum computing. One of the most exciting applications of quantum mechanics is quantum computing. Unlike classical computers that use bits, quantum computers use qubits, which can exist in superposition. This unique property allows quantum computers to perform complex calculations at incredible speeds. Medical imaging. Quantum mechanics is also essential for medical imaging. MRI, or magnetic resonance imaging, uses principles of quantum mechanics to create detailed images of the human body. This technology has revolutionized medicine, allowing doctors to diagnose conditions without invasive surgery. Today, quantum mechanics remains a hotbed of research, with scientists exploring its potential to reshape our future. Quantum cryptography is being developed for ultra-secure communication, and quantum sensors are being designed for extreme precision. Quantum mechanics is more than just a theory. It's a gateway to a new era of technology and understanding. Quantum mechanics challenges our understanding of reality, pushing us to rethink everything we thought we knew. Thank you for joining us on this journey through the quantum realm. If you enjoyed exploring the mysteries of physics, don't forget to subscribe for more insights into the wonders of science.